Okay, so when alpha is 0, cosine of alpha, what happened to cosine of alpha is 1. If alpha is, of course, 180 degrees or pi, cosine of alpha is -1. And here, cosine of alpha is 0, right? Now, if cosine of alpha is 1, guess what? Okay, the directional derivative is exactly the magnitude of this, right, times 1, okay? And it has to be the maximum of all directions, okay? Because, I mean, cosine of alpha, this thing cannot be bigger than 1. So that means the directional derivative of f at this point, x naught, y naught, cannot exceed this value here. And that happens only when the angle is 0. Now, what does angle 0 mean? This means, okay, so you remember this is the, if this is your gradient, okay, and if this is your unit vector, the angle 0, when angle alpha is 0, that means that the gradient is in the direction of u. So the direction that was specified happens to be in the direction of the gradient, right? So this means u is in the direction of the gradient of f. Okay, and so so basically what I'm saying is that the directional derivative becomes maximum in the direction of the gradient itself, right? When u is and of the same direction as the gradient. So the direction, and I'll write this down in a moment. The directional derivative is maximum in the direction of the gradient itself, and in that direction, the maximum magnitude is this, the magnitude, or the maximum rate of change is the magnitude of that gradient. Right. Now, this is basically, the second one is opposite. This is not as important. Here, basically, this is saying that if you go in the opposite direction, then you get the minimum. Okay, so in other words, if the maximum rate of change is 5, for instance, okay, then you go in the opposite direction and the rate of change will be -5. But that's sort of well understood, right? I mean, if you turn around and start going in the other direction, opposite direction, the rate of change, of course, becomes the negative of what it used to be, right? Now, the third one is also quite important. Right? What happens if this part is 0? Well, it's simple. Then the gradient, well, the directional derivative will be 0. Okay, and this happens when? This happens if the this angle is 90 degrees. So this happens if u is perpendicular to the gradient, right? And what happens if the directional derivative is 0? Okay, this means it's tangent to the level curve through the point. You remember what level curve is? Yeah, the level curve, if you have this level curve here, and if this is x naught, y naught, level curve, well, here, let me just make this a little simpler. If this is a level curve, going through x naught, y naught, right? Then the level curve means that it means exactly what that is. It's a level curve. So along this line, the value z, f of xy, does not change, which means the derivative, the rate of change in that direction is 0, right? And that is perpendicular to the, so what I'm saying here is that this tangent line is perpendicular to the gradient, and the gradient is going to be something like this. Okay, so this illustrates two very important facts, which I'm about to write. Okay, so this is you can call this a theorem, and this is one of the most important theorems that you will learn in chapter 4. So make sure you note this, memorize this, eat it, digest it, make it a part of you. Okay. So the reason this gradient is so important is this, and I'll set this up correctly here. If f of xy is differentiable, at x naught, y naught, In other words, the derivative exists, right? So first, the directional derivative at x naught, y naught is the gradient evaluated at x naught, y naught dotted with u. Okay, so this is, of course, the first thing I said. And then second, remember this gradient is a fixed vector, right? In other words, for every x naught, y naught, you can evaluate the gradient, which is going to be a two-dimensional vector. And you can draw this vector on the domain, which is a two-dimensional plane at x naught, y naught, right? And so what this is saying is, if you go in the direction of u, which is the direction of the gradient, if u happens to be showing you the same direction as the gradient, then the directional derivative is maximum. Right? So this points to the direction of the maximum rate of change. Did you get that? Of f at that point. Okay, so this is actually, I mean, you know that the gradient is an arrow, right, a vector. And it's showing you, hey, this way, if you want to maximize the rate of change. Okay, in other words, this is the steepest direction in which you can walk if you are in a hurry to get, you know, to the higher elevation. Or if you want to maximize the rate of change of f, this is the direction in which you should walk. Right? That's what this is saying. And furthermore, the gradient evaluated at x naught, y naught has this magnitude because it's a vector, and that magnitude is that, I mean that as in the demonstrative pronoun, is that maximum magnitude or maximum rate of change. All right, so the reference here is in line 2 or in part 2, I said, the gradient points to the direction of the maximum rate of change, right? And this maximum rate of change, what is that maximum rate of change? What is the numerical value of that maximum rate of change at x naught, y naught? You know, is that like 10 or 20 or what? Well, that maximum rate is the magnitude of the gradient, okay? So look, you know, gradient. I mean, a gradient is a vector, right? It has a direction and a magnitude. The direction shows you the direction of the maximum rate of change, and the magnitude shows you that maximum rate of change. This is a powerful tool, right? Gradient is extremely important because of these, actually all three of these properties. Okay, so you probably have the idea by now that in section 4.6, I said 4.6 is probably the most important section in chapter 4, and perhaps in all of calculus 3. And that's because we introduce you to this concept of gradient. Okay, now spend a lot of time with gradient. I know you just met, but spend a lot of time, think about gradient, dream about gradient, you know, and just try to spend some good quality time with the gradient of f, and then you will get to know him or her, whichever you consider, and then you will understand, okay, and you will just sort of really just understand this gradient as you spend time. So it is very important for you to do that. All right. Okay, so now let's go to the next. Okay, so one last thing here, and I almost forgot to say this, but this last thing here says if the angle between the gradient and the direction specified is perpendicular, then the gradient dot u becomes 0, which means that you're not going up or down, which means that you're going in the direction of a level curve, right? So this is always perpendicular to the level curve through x naught, y naught. All right, now you may have a clear understanding of what's happening here. You may have not clear idea of what's going on. Let me explain this. Okay, maybe I will, let me give you an example. Maybe this example will help, right? So this is the example, which is symmetric, so you can clearly understand this. It is 4 minus x squared minus y squared. okay? And let's pick a point 1, 1. Okay, so now f of 1, 1, for instance, is 4 minus 1 square minus 1 square. Of course, it's 2, right? Okay, try to draw a picture of the graph of this function in XYZ, the three-dimensional plane, three-dimensional space, okay? And I want you to find the gradient. And let's find out what that gradient tells us, okay? So you can pause this if you like, and then you can come back and try to figure out what this is saying. First, I would encourage you to sketch the graph. Go. Okay, so you figure this is a upside down bowl or a circular paraboloid, right? And we found the point, which is 1, 1, 2. And now what's next? Okay, let's find the gradient. Okay, remember, this is all you have to do is to find fx and fy. In this case, it's super easy, right? Because it's negative 2x, negative 2y. If you evaluate this at 1, 1, you basically get negative 2, negative 2. All right, so, and I have this picture here. This is 2. This is 2. Let's say here's the point 1. So the, you know what, I should draw another picture of this. The gradient that goes through this point, how do I do this? Maybe this will, that's not the way to work. I'll try to make it a little bigger. I think this may be better here. Yeah, okay. So what I wrote, what I drew, this is, let's go ahead and do this. This is the level curve where f is equal to 2, okay? And it does go through the point 1, 1 because, you know, this graph goes through the point 1, 1, 2, right? So the level curve of f is equal to 2 is the circle centered at the origin of what is the radius square root of 2, I guess, right? Because 1, 1 is in there. All right, so what does it tell us? Well, can you tell what the gradient is doing? And the gradient is negative 2, negative 2. So if I were to draw a gradient here, this is my gradient. It goes in the direction of negative 2, negative 2. Okay, so the blue, what I wrote in blue, what I just drew, wrote in blue. Okay, so the gradient at the point 1, 1 is negative 2, negative 2. Notice here I use parentheses to indicate the point and the angle brackets to represents the vector, right? So this is my gradient. And what this gradient is showing is the magnitude of the square root, magnitude of the gradient. And that's negative 2 square plus negative 2 square, and that's the square root of 8, which is 2 square root of 2. Guess what? This is the maximum rate of change of this function as you're standing at 1, 1, 2. Okay. Now, so what this is saying is, you know, you can start walking in this direction, or climb up, you know, your wall this way, or you can go down in this direction. And then if you're asking, in which direction should I go in order to maximize my rate of change? And the answer is you go toward the origin. And in fact, if I were to graph this gradient in this picture, you'll be going in this way, going straight through the origin, okay? And that means you go toward the middle. If you're standing here, you climb up toward the middle to the, you know, to the highest point here. That is the direction of that maximum rate of change. What else? So I would say that negative 2, negative 2 is the direction of the maximum rate of change. Okay, so I think this illustration helps you understand this, I think, much better than just all the theoretical thing here. Okay, a good illustration, a good example is worth 1,000 words. And so once you find the gradient, okay, which at each point is a specific two-dimensional vector that is showing you the direction in which to maximize your rate of change, and the value of that maximum rate of change is the magnitude of that gradient itself. Okay. Now you notice here, this is perpendicular or orthogonal to what? To the level curve, right? The level curve is the red circle, and so you can see it's perpendicular, and that's because again the directional derivative and the level curve, meaning that you are not going up or down, they are tangent, they are perpendicular to each other because the dot product is equal to 0. All right, so that's the picture. Now maybe I can illustrate this again. If you have a two mountain topography like this, you know, your let's say you have a geographic place like this, and sort of like what you see around here, you have lots of these hills. If you are to, let me use the same color as before. If you are to draw some level curves here, it will be, and by the way, level curves are sometimes drawn on the surface itself, but typically it's drawn on the plane, which is the part of the domain, right? And so you can see that this is what the level curves look like, right? You know, basically what you're doing is connecting all of these points here and then projecting them down to this point, right? So if you're standing, for instance, right at this point, maybe over here, okay, then the gradient will be pointing in this direction perpendicular to the level curve at this point and showing you the way up. In fact, the way to go fastest in terms of changing your altitude, right? Increasing your altitude. If you're over here, then it'll be pointing this way. Not necessarily to the center, but it is perpendicular to it. Okay, it is perpendicular to the angle. If you're standing right here, okay, it'll be perpendicular to the level curve at this point, right? If you're here, it's going to be perpendicular again to this point, and so on. If you're right here, then it'll be perpendicular to the level curve. Okay, and so if you keep following the level curve, then eventually you'll go to the top, but that may not be the straight line. Okay, so that's the point here. Now let me give you another example, and then you can maybe pause this and then try to figure this out. Here's the question that I am going to ask you to do. Let's say f of xy is x cubed minus x e to the 2y, okay? And the question is, at the point 1, 0, number 1, find the direction of the maximum increase. And by the way, what I mean by increase is, of course, the rate of change, right? Find the direction of the maximum increase, and that means that you are to give me a vector that shows this direction, hopefully the unit vector, right? And then find that maximum rate of change. So in the first one, I'm asking you, which direction should I go if I were to get the maximum rate of change? And number 2, what is that maximum rate of change? You know, what is the value of that maximum rate of change? And number 3, draw the level curve through this point and the gradient at this point. Okay, so let's see if you can do all of these, and maybe I should do one more thing. Number 4, find the vector tangent to the level curve at 1, 0. Okay, so there are several things you have to do here, and maybe again you may want to yeah, actually try to draw a vector, draw a level curve. Okay, maybe that may be the thing you are interested in doing first. But anyway, find the answers to these 4 questions, and when you think you do, you can come back and go to the next segment of this lecture video.